LZ77 and LZ78 from Wikipedia, the free encyclopedia. LZ77 and LZ78 are the two lossless data compression algorithms published in papers by Abraham Lempel and Jacob Ziv in 1977 and 1978. They are also shown as LZ1 and LZ2 respectively. These two algorithms form the basis for many variations including LZW, LZSS, LZMA, and others. Besides their academic influence, these algorithms form the basis of several ubiquitous compression schemes, including GIF and the deflate algorithm used in PNG and zip. They are both theoretically dictionary coders. LZ77 maintains a sliding window during compression. This was later shown to be equivalent to the explicit dictionary constructed by LZ78. However, they are only equivalent when the entire data is intended to be decompressed. Since LZ77 encodes and decodes from a sliding window over previously seen characters, decompression must always start at the beginning of the input. Conceptually, LZ78 decompression could allow random access to the input if the entire dictionary were known in advance. However, in practice, the dictionary is created during encoding and decoding by creating a new phase whenever a token is output. However, in practice, the dictionary is created during encoding and decoding by creating a new phrase whenever a token is output. The algorithms were named an IEEE milestone in 2004. Contents: 1. Theoretical efficiency. 2. LZ77 2.1 pseudocode. 2.2 implementations. 3. LZ78. 4. See also. 5. References. And 6. External links. Theoretical efficiency. In the second of the two papers that introduce these algorithms, they are analyzed as encoders defined by finite state machines. A measure analogous to information entropy is developed for individual sequences as opposed to probabilistic ensembles. This measure gives a bound on the data compression ratio that can be achieved. It is then shown that there exist finite lossless encoders for every sequence that achieve this bound as the length of the sequence grows to infinity. In this sense, an algorithm based on this scheme produces asymptomatically optimal encodings. This result can be proven more directly, as for example in notes by Peter Shore. LZ77. LZ77 algorithms achieve compression by replacing repeated occurrences of data with references to a single copy of that data earlier in the uncompressed data stream. A match is encoded by a pair of numbers called a length-distance pair, which is equivalent to the statement each of the next length characters is equal to the character's exactly distance characters behind it in the uncompressed stream. The distance is sometimes called the offset instead. To spot matches, the encoder must keep track of some amount of the most recent data, such as the last 2 KB, 4 KB, or 32 KB. The structure in which the data is held is called a sliding window, which is why LZ77 is sometimes called sliding window compression. The encoder needs to keep this data to look for matches, and the decoder needs to keep the data to interpret the matches the encoder refers to. The larger the sliding window is, the longer back the encoder may search for creating references. It is not only acceptable, but frequently useful to allow length-distance pairs to specify a length that actually exceeds the distance. As a copy command, this is puzzling. Go back 4 characters and then copy 10 characters from that position into the current position. How can 10 characters be copied over when only 4 of them are actually in the buffer? Tackling one byte at a time, there is no problem serving this request, because as a byte is copied over, it may then be fed again as input into the copy command when the copy from position makes it to the initial destination position. It is consequentially fed data that was pasted from the beginning of the copy from position. The operation is thus equivalent to the statement, copy the data you are given and repetitively paste it until it fits. As this type of pair repeats a single copy of data multiple times, it can be used to incorporate a flexible and easy form of run length encoding. Another way to see things is as follows. While encoding for the search pointer to continue finding matched pairs past the end of the search window, all characters from the first match at offset D and forward to the end of the search window must have matched input, and these are the previously seen characters that comprise a single run unit of length L sub R, which must equal D. Then, as the search pointer proceeds past the search window and forward, as far as the run pattern repeats, in the input, the search and input pointers will be in sync and match characters until the run pattern is interrupted. Then L characters have been matched, in total L greater than D, and the code is square bracket D, comma L, comma C, closing square bracket. Upon decoding, open bracket, D, comma, L, comma, C, close bracket, comma, again, comma, D equals L subscript R. When the first L subscript R characters are read to the output, this corresponds to a single run unit appended to the output buffer. At this point, the read pointer could be thought of as only needing to return int L divided by L subscript R plus 1 if L mod LR not equal to 0 times to the start of that single buffer run unit, read L subscript R characters, or maybe fewer on the last return, and repeat until a total of L characters are read. But mirroring the encoding process, since the pattern is repetitive, and read pointer need only trail in sync with the write pointer by a fixed distance equal to the run length L subscript R until L characters have been copied to the output total. Considering the above, especially if the compression of data runs is expected to predominate, the window search should begin at the end of the window and proceed backwards, since run patterns, if they exist, will be found first and allow the search to terminate. Absolutely if the current maximal matching sequence length is met, or judiciously if a sufficient length is met, and finally for the simple possibility that the data is more recent and may correlate better with the next input. Pseudocode. The pseudocode is a reproduction of the LZ77 compression algorithm sliding window. While input is not empty, do prefix : equal longest prefix of input that begins in window. If prefix exists, then I : equal distance to start of prefix, L : equal length of prefix, C : equal char following prefix in input. And if prefix does not exist, I : equals 0, L : equals 0, C : equals first character of input. Output, and then within parentheses, I, L, C. S : equals pop, L plus 1 chars from the front of input. Discard L plus 1 chars from front of window. Append S to back of window. Repeat. Implementations. Even though all LZ77 algorithms work by definition on the same basic principle, they can vary widely in how they encode the compressed data to vary the numerical ranges of a length-distance pair, alter the number of bits consumed for a length-distance pair, and distinguish their length-distance pairs from literals, raw data encoded as itself, rather than as length of a length-distance pair. A few examples. Bullet point. The algorithm illustrated in Lempel and Ziv's original 1977 article outputs all its data 3 values at a time: the length and distance of the longest match found in the buffer, and the literal that followed that match. If 2 successive characters in the input stream could be encoded only as literals, the length of the length-distance pair would be 0. Okay. LZSS improves on LZ77 by using a 1-bit flag to indicate whether the next chunk of data is a literal or a length-distance pair, and using literals if a length-distance pair would be longer. In the Palm doc format, a length-distance pair is always encoded by a 2-byte sequence. On the 16 bits that make up these 2 bytes, 11 bits go to encoding the distance, 3 go to encoding the length, and the remaining 2 are used to make sure the decoder can identify the first byte as the beginning of such a 2-byte sequence. In implementation used for many games by Electronic Arts, the size in bytes of a length-distance pair can be specified inside the first byte of the length-distance pair itself, depending on whether the first byte begins with a 0, 10, 110, or 111. When read in big endian bit orientation, the length of the entire length-distance pair can be 1 to 4 bytes. As of 2008, the most popular LZ77-based compression method is deflate. It combines LZSS with Huffman coding, literals, lengths, and a symbol to indicate the end of the current block of data are all placed together into one alphabet. Distances can be safely placed into a separate alphabet because a distance only occurs just after a length. It cannot be mistaken for another kind of symbol or vice versa. LZ78. LZ78 algorithms achieve compression by replacing repeated occurrences of data with references to a dictionary that is built based on the output data stream. Each dictionary entry is of the form dictionary open square brace ... close square brace equals open curly brace index comma character close curly brace, where index is the index to a previous dictionary entry, and character is appended to the string represented by dictionary open square bracket index close square bracket. For example, ABC would be stored in reverse order as follows: dictionary K equals tuple J and C. Dictionary J equals a tuple I and B. Dictionary I equals a tuple 0 and A, where an index of 0 specifies the first character of a string. The algorithm initializes last matching index equals 0 and next available index equals 1. For each character of the input stream, the dictionary is searched for a match. The last matching index character. Okay, so this is a curly brace last matching index comma character. For each character of the input stream, the dictionary is searched for a match, colon, open curly brace, last matching index, comma, character, close curly brace. That's a tuple. If a match is found, then last matching index is set to the index of the matching entry, and nothing is output. If a match is not found, then a new dictionary entry is created. Dictionary, open square brace, next available index, close square brace, equals tuple last matching index, comma, character. And the algorithm outputs last matching index followed by character, then resets last matching index equals 0 and increments next available index. Hold on, let me scroll down here for a second. Once the dictionary is full, no more entries are added. When the end of the input stream is reached, the algorithm outputs last matching index. Note that strings are stored in the dictionary in reverse order, which an LZ78 decoder will have to deal with. LZW is an LZ78-based algorithm that uses a dictionary pre-initialized with all possible characters, symbols, or emulation of a pre-initialized dictionary. The main improvement of LZW is that when a match is not found, the current input stream character is assumed to be the first character of an existing string in the dictionary, since the dictionary is initialized with all possible characters. So only the last matching index is output, which may be the pre-initialized dictionary index corresponding to the previous or the initial input character. Refer to the LZW article for implementation details. BTLZ is an LZ78 based algorithm that was developed for use in real-time communication systems, originally modems, and standardized by CCITT/ITU as V.42BIS. When the trie-structured dictionary is full, a simple reuse/recovery algorithm is used to ensure that the dictionary can keep adapting to changing data. A counter cycles through the dictionary. When a new entry is needed, the counter steps through the dictionary until a leaf node is found, a node with no dependence. This is deleted and the space reused for a new entry. This is simpler to implement than LRU or LFU and achieves equivalent performance. So it kind of sounds like similar to a sliding window concept, except the dictionary itself is changing over time. That's kind of what that sounds like. I could be wrong. The dictionary is either changing over time or it's growing over time. I don't know. Okay, so let's see. See also Lempel-Ziv stack, LZS, discrete cosine transform, DCT, a lossy compression algorithm used in JPEG and MPEG coding standards. And we have some references, which I will skip reading just because I don't think it's conducive to my use of time. External links, I think, are somewhat valuable to read because they kind of give you an idea of where to go next. I mean, references, I guess, could as well, but they're a little bit more esoteric, I find. External links, the LZ77 algorithm, Data Compression Reference Center, RASIP Working Group, Faculty of Electronic Engineering and Computing, University of Zagreb, 1977, archived from the original on 7 January 2013, retrieved 22 June 2012. Bullet point, the LZ78 algorithm, Data Compression Reference Center, RASIP Working Group, Faculty of Electrical Engineering and Computing, University of Zagreb, 1997, archived from the original on 7 January 2013, retrieved 22 June 2012. Bullet point, the LZW algorithm, Data Compression Reference Center, RASIP Working Group, Faculty of Electrical Engineering and Computing, University of Zagreb, 1997, archived from the original on 7 January 2013, retrieved 22 June 2012. And then we have a list of data compression methods, which I don't find conducive to read, so I'm just going to scroll through all of these. Because I'm only really concerned with like this deflate and LZW, and if PNG somehow shows up in here, that would also be something I would be concerned with. But everything else I'm not concerned with, and I'm not going to remember all of these acronyms, so it's just pointless for me to read. Okay, so categories, lossless compression algorithms, and Israeli inventions, oddly enough. Okay. This page was last edited on 21 February 2020 at 15:08 UTC. This text is available under the Creative Commons Attribution Share Alike license. Additional terms may apply. By using this site, you agree to the terms of use and privacy policy. Wikipedia is a registered trademark of the Wikipedia Foundation, Incorporated, a nonprofit organization. So that is the end of the LZ77 and LZ78 article on Wikipedia.